All right, so 46. Oh yeah, this is one of my favorites. All right. And yes,
That's usually bad.
yeah, I was about to say something along those lines. But no, once you see this, it's kind of cool. Because a big part of this, I think I said this last time, a big part of this is realizing what you're allowed to do, what you're able to do. What's wrong, fundamentally, it's kind of good to me. If you think you can't do this problem, it's actually a good sign, even though you can't. But this is the kind of problem, let's see, what do I have, square root of x plus 2? 2 plus x? Huh? What's kind of fundamentally wrong with this if I want to use u sub? In fact, I pretty much have to use u sub. What's... In order to be able to use u sub, it's kind of like the chain rule. So you would let u equal to the inside dude. And then you'd hope to God that somewhere outside, free to move around, because the whole idea of u sub is, I want to put the stuff on the outside together with dx. And that would be du. So what's fundamentally wrong here? Degree-wise, right?
Yeah.
The thing on the inside, is its derivative out here? No, shit. Well, in a way it is, because its derivative is 1. But it's not useful. I can't get rid of it. If this was inside and this was outside, somehow that'd be better. Right? So, real quick little side example. Here's what u sub normally works like. Here's a very standard kind of u sub problem, right? And this is exactly what you're looking for. This is going to be an example of how you can modify. You can use u sub to make things happen. That's good. So I'll actually do 2 side examples. That's beautiful. That's classic u sub, right? Of course, you know, it's not classic to us. We've only known it for so long. But what's nice about this? What's the inside function? Yeah, x squared minus 2. It's definitely the inside function, no question. Is its derivative basically in there, minus a coefficient, because we don't care about coefficients. We can make them show up all day long. Yeah, because its derivative is basically x. With a 2 coefficient, but who cares? You guys kind of with me? So that's what's important, is the real heart of it. The stuff, you can add the others, you can add the coefficient in, that's no big deal. So if you let u equal this inside dude, what's du? 2x dx. So I need a 2x dx. I have an x dx. So you see how this dude is free to move over there? I could put him over there if I wanted to, right? So the inside dude is going to be u. The outside dude is the one that can move around. So you hope to God he's related to du. Because the whole point of this is to rewrite that integral with respect to x to become an integral with respect to u. You want to replace all the x stuff with u stuff. So, this problem's not that bad. What do I need here? 2. So what am I going to put outside? To balance. So this 2x dx is du. And this becomes square root of u. So I'll write it as u to the 1/2. And then what's the integral of u to the 1/2? What's the integral of u to the 1/2?
X squared minus 2.
What's happening? This is the integral of u to the 1/2 du. So right now on this step, I don't care what the hell happened before. I am being faced with an integral with respect to u. And what's the integral of something to the 1/2 power? Yeah, 3s power, so 2/3 outside. But now you bring back in, what is u? What do u be? X, now u is x squared minus 2. Right? And then you can simplify this. And of course, don't forget your little plus c dude. Okay, so that's how u sub normally works. Oh, what did I do with the 3/2? Oh, thank you. I felt something was not there. Thank you. So all I did was replace u with what it is. So yeah, that better still be there. Simplified, and I'm done. So that's normally the way u sub works. When there's a function caught inside some other function. That's exactly chain rule, right? So this is integral's response to chain rule. In order for the integration to work, when I do chain rule, I suddenly have an outside piece show up. You with me? That wasn't there before, because that's what chain rule does. It lets the inside get a turn. So integration needs that outside piece to be there to be able to work backwards. That inside piece, that outside piece gets sucked back in. Because if I took the derivative, this is what would happen. The 2x would come popping out. Right? Okay. Some of you guys are less than impressed. That's okay. The second side example is not this stuff. I forgot what my point was with the second dude. Screw it. So, so this guy is what we got to work with. And there's really no way to escape you being this. Here's my second example. There. I'm a little OCD about this. It's going to keep bugging me then. In 2 different classes at once. It's freaking me out. Okay. If I had this, why can I do this without using any U sub or any weirdness at all? Do I need any U sub or anything? I can just multiply it in and blah, blah, blah. It's easy. I'm not even going to do it because that's too easy to even do. Right? It should be. Some of you guys are having some trouble on some of those problems on the quiz, but I mean, maybe I should do this. So if you multiply this in, what do you get? 7.5, I like it. Plus 4x to the 3/2, and then that should be easy. Oops, if I do the integration, I get x to the 9/2. 2/9, I like it. Plus, 4x to the 5/2, so it has 2/5 on the outside, and then you clean it up and blah, 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 and there's your plus c. Okay, everything's nice and happy, right? So somehow those two things come together in this one problem. I cannot integrate that the way it sits, and it looks like I cannot use U sub. But U sub is cool. U sub can change what something looks like. Why can't I do what I did here with this? Because my thing to the 1/2 power is not just x. This was easy because there's just x to the 1/2. It can go in there and it can combine with the other stuff. Are these the same base? No, shit, I can't do that same thing. Damn it. But if I let u equal to 2 plus x, what's du? dx. And what's x? If u is 2 plus x, x is u minus 2. So the name of the game with u sub is substitution. That's why it's part of the name. I want to substitute everything that is currently x with something that is u.
Can you explain how you got u again?
How I got what now?
Sorry. U minus 2, x is u minus 2.
Well, because if u is 2 plus x, subtract 2, x is u minus 2. That's all, right? So this is kind of funny, and this is a little evil, so I'm not saying you should have known this or something. But anytime if I let u equal 2 plus x, it's just a fact now. The minute I write that down, therefore x must be u minus 2. There's no escaping that. That's algebra. You can't escape it. What's nice is you can use it. What happens here? Now it's going to become something like this. X squared becomes
U minus 2 squared.
U minus 2 squared. Square root of 2 plus x is now square root of u. So u to the 1/2. Now it looks a lot more like that did, right? That's the thing with u sub that we don't even know we could do. And what did I miss here? Du is dx. That kicks ass. Sorry, just replace dx with du. You cannot have any x's left when you're using u sub. It's got to be all x and then all u. You can't have an x just laying around. You can't just bring an x outside because now it's all u's. Let me bring an x outside. No. Right, u is a function of x. They're in. You can't just take. It's not a constant. You guys kind of with me? Shit, there's one more thing I was going to say. I forgot. So now you just FOIL this out, distribute that. It'd be a lot like that problem. Is that semi-decent? So if I want to finish this out, I get integral u to the 1/2 times u squared minus 4u plus 4 integral u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2. I mean, is that cool? And that's not that bad, right? You guys see with me? Not time for poker face. You guys with me? And not time for lying either. And just to finish this out real quick. What would you get? U to the 5/2 integrated is u to the 7/2, so it's got a minus 4u to the, what would be 5/2, right? And then 2/5 out there, plus 4u to the 3/2 with the 2/3, and then plus c. And the last thing you always have to do, the original question had x's in it, so your answer better have x's in it, so don't forget at the end to substitute back in, right? U is just a middleman here. That's what u do be. And I can't remember if I did, so the last thing here would be 2/7. U was 2 plus x, just put a 2 plus x in there. Minus 8/5, blah, 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 blah. Right, just put the 2 plus x back in. Is that cool? Semi-decent? Because I can't remember now if I showed you something like 1 over x minus 2 ln x squared minus 5 times 1 over x minus 2 ln x plus, let's see what you got, Jeff. Minus 24. Factor that, right? This is the first place you might see u sub, depending on who your teacher is. If you let u equal to 1 over x minus 2 ln x, then this suddenly looks very easy, right? That's the first place you see u sub. The reason it's a little different now is I don't just have stuff here like that to replace with u. I also have to have some derivative idea so that I can replace dx also. That's the kind of like extra step added here. Okay. I really went off on that one. And as long as we're on the topic, before I go to any more questions, let's finish something out about u sub. You guys got all this here? Okay. How does u sub interact with limits on my integral? So it's a definite interval. That was an indefinite interval. Everything I did up here just now was indefinite because it didn't have any boundaries, right? No a and b. So what would u sub do if I had like 1 to 8? Oh, what you got, Jeff? I don't know. There, look out. I'm fine, that looks gross enough. A lot of functions are very easily identifiable. A lot of integrations are easily identifiable as u sub. Because you can see, I see a cube and I see a squared. Those are related by derivatives. And sure enough, the cube is in the right place, and even if it wasn't, I might be able to do something like I just did in the last problem. Use u sub kind of indirectly. I don't have to do that. I can use it exactly. This is a classic u sub problem. The only thing is I got these guys. So let me first show you, I'm trying to figure out which way. I'm going to show you what I do, and then I'll show you what the book does. And those are not, I do it. It's actually a method I made up myself. And I made it up way back when they first taught this to me because I just didn't want to do what they said I should do. And then I'll show you the book method in case you're scared to do it. They both are mathematically equivalent, so we'll see what you guys think about it. So what the book says, okay, what would I have to let u equal in this case?
2 minus x.
2 minus x cubed, what's du? Yeah, negative 3x squared, so what am I, dx. So what am I missing inside to make that du okay? Yeah, so I need a negative 3, so I need a negative 1/3 on the outside to balance that. Is that cool? Now, real quick, the way, why am I showing you this? No, screw it, I'm not going to show you. I can't remember, the book shows you. You can solve for dx, but that gets you in trouble. Because then you might not have what you need inside. If I solve dx, and then I throw this in place of dx, you better hope you got what you need in there. And this is what leads people to trouble. So in one sense, it's easier. But in another sense, that wasn't that hard. And it doesn't make you in trouble. I can see exactly that I have what I need. When teachers teach this from the beginning, students just start throwing it in there without thinking ahead. Do I have what I need there? And then that's when they have like an extra x left over. Everything's u except one x left over. Oh shit, well just take it out. You know, that's... And I hate that. So I don't like teaching that way, but if that makes any sense to you and you like it, you can do it that way. Just don't make any mistakes or I'll take a lot of points off. So what do we got? Now, there's one mistake with this in a way, the minute I start replacing it with you, because what does this tell me? What do those mean? What are those there for? What do they relate to?
1 to 8.
1 to 8. What 1 to 8?
X.
X goes from 1 to 8. So what am I going to do next here? I'm going to rewrite this. This whole thing is du. This now is the cube root of u. So u to the 1/3. But if I do this, I am wrong. Because, unless u is x or something, or they just happen to have the same values, x goes from u to 8. But what does u do? Well, I have to plug that in to see what u does. Right? So what I do, that's what the book does. What I do is just do this. I just say, I'm just holding the place. That's not really u stuff. Because what am I going to do before I plug these in? These aren't for u, these are for x. So what am I going to do? What I always do, I'm going to put it back in terms of x. So to me, that just made more sense as a student. That's what we do when we have indefinite intervals. Why shouldn't I do the same damn thing? Bring it back to x. It's the same math. So let me do it my way, and then we'll do it the book way, and we'll see what happens. So what is the integral of u to the 1/3?
3/4.
Yeah, it'd be u 4/3, so 3/4 from not quite 1 to not quite 8. All right, not quite ready for prime time. So we got negative 1/3. Well, now I can simplify this a little bit. I got negative 1/4. What's u?
2 minus x to the 3.
From 1 to 8. Now I can take the parentheses out because that's what x does, and x is back. So this would be negative 1/4, 2 minus 1, minus negative 1/4, 2 minus a cubed, whatever the hell that is. Oh, I can't think. 5, is it 5/20? Yes, okay then. And now you just do all that crap. Is that semi-decent? You guys with me? This is like big ass F of 8. Why did I just do that backwards? Jeff? That's my bad. Try to keep everything else's track. So it should be negative 1/4, 2 minus 8 cubed, minus, it's always got to be big ass F of 8, minus big ass F of 1. That's the fundamental theorem of calculus part 2. And then, so minus negative 1/4, 2 minus 1 cubed. And then you just do all that stuff. Is that decent?
It's definitely easier than how the book does it.
Huh?
It makes way more sense than how the book does it.
And just to show you, I mean, actually the amount of math is about the same. But I always hated the disconnect between what we do, with the indefinite. I don't know if that made any sense. But the way the book, and most, everybody, this is not a huge thing, by the way. This is just a little, whatever. A lot of people would be very upset about this. But we do very similar things in other parts of mathematics. I mean, that's what's the matter. The whole problem, they say, is that's not really the limits for that. So you must change it. But who cares? The math doesn't care. So what they would say is, the minute you start putting u in here, then you have to have the limits. If x is 1, u would be 2 minus 1, 1. If x is 8, u would be 2 minus 8 cubed, which I think we figured out was negative 510. Right, 2 minus 512. You with me?
Did you write u of 8 at the top and u of 1 at the bottom?
Yeah, but even better. I like that. Well, yeah, that would work. Use a function of x. That would work. Me, I'm not going to do that. That might make them feel a little better, but me, that's fine for me. And then, so what you would do here is instead of integrating with u and changing it back to x, you stay with u and you change these from x to u. If x goes from 1 to 8, u goes from 1 to negative 5, 10. And then you just integrate that. But see, mathematically, I'm going to end up with a negative 5, 10 right there. I mean, the math doesn't care. It's the same exact thing. But to me, it just makes more sense to do this. It's not even me being lazy because I'm doing the same amount of work. So I hope to God that didn't confuse anybody. I mean, it's just a choice you can make. You can either do it just like the book does and leave the u's and then just plug that in. So when you integrate this, you'll get negative 1/3 u to the, I left some out. U to the 4/3, 3/4. So you'll evaluate that between 1 and negative 5, 10. Right? Or you can instead leave these in terms of x and just take it back to x and then just plug those in. Either way. So that's the one piece I left off of use of discussion was what to do with the limits.
No, does it not matter if the larger number is on bottom?
Doesn't matter at all. All it means is my integral is going to come out probably negative here possibly, but see the integral, the definition of integral really doesn't matter if a and b, if one is bigger than the other or vice versa. It doesn't care. What I do know is that this is how related to this. Good. Right. So if I wanted to flip it back around, I could just make it positive 1/3 integral from negative 5, 10 to 1. You guys with me? So you always have that option. Multiple negatives kind of make things weird, especially because the fundamental theorem of calculus part 2 says f of b minus f of a, and you got another negative there, they always get freaked out. So if you ever want to just suck that negative in and just change the limits around, completely optional. Okay. I like to look at some of your faces. Any other specific questions from homework that I can take way too far? Yeah.
Number 60 is 5.5?
Sorry, which one?
60?
60? Oh yeah, this is, I keep saying this, but this is a classic problem. If I saw this in there, I know what has to be there for me to be able to do this. Something related to what's got to be here.
Negative 2.
What's the derivative of negative x squared? Negative 2x. There's got to be at least an x there, and there is in this problem, thank God. Right? Because again, the inside function has to have its derivative out there with it, right? That's the whole idea. You guys, I can't read you anymore. I don't know if you've changed or I've changed. My eyes, I don't know. I can't read you guys anymore. And this is from something to something?
Yeah.
0 to 1.
1.
So, how do you use u sub? This is a good example of what we just did here. U would have to be what?
Negative.
Yeah, the inside function, du is negative 2x dx. I like it. And u sub is a little weird because you have like an integration problem, but in the middle of it you have to do a derivative. So I understand changing gears is difficult in the middle of the problem. Does that make sense? You're thinking integration. It's an integration problem, but in the middle of it you got to do a derivative. So sometimes I see people put here x cubed over 3, and then that freaks them out, and they're like, what the hell? They actually integrate instead of differentiate. So be careful. So what am I missing? Yeah, I need a negative 2x dx. So if I put a negative 2 there, I got it, but I better put negative 1/2, or else I just totally changed my problem. So now, in terms of u, I have negative 1/2 integral sort of 0, sort of 1. If you want to do it my way. If you don't like my way, When x is 0, u is 0. When x is 1, u is negative 1. So it'll be 0 to negative 1. Either way, I don't care. Either way. They really are about the same amount of work. And if you like this way, please, dear God, don't make me feel like, don't think I'm trying to tell you you can't do it that way. There's not a damn thing wrong with that way. It's the same amount of work. It's just a slightly different perspective on it. Nothing wrong with this way at all. Not a damn thing. Because I'm going to do the same math work here that you're doing there. Who cares? What happens to the inside? Negative 2x dx is du. And of course, e to the negative x squared is now. And that kicks ass because the integral of e to the u is e to the u. U was negative x squared. And I want to go from, I don't need my parentheses anymore because I brought my x back in. Is that cool? I resubstituted for u in the middle there. I didn't show that step explicitly. But this integral is e to the u. And then I replaced u with what it is. So then I get negative 1/2 e to the negative 1. Just plug a 1 in. Minus negative 1/2 e to the 0. So I get negative 1/2. I can put my negative 1 over 2e plus 1/2. I like it. So don't fall into the trap where people see the 0 and they think that, I'm not even going to write anything because it's a 0 I'm plugging in. But when you plug a 0 in, you get a 1 here. So that stays there. So be careful about that. We get so used to polynomials. When I integrate polynomials, I never have to worry about 0, really. Unless there's like a 1 over x in there and the whole thing freaks out. But I never have to worry about zeros because it's going to make the whole thing 0. But it totally depends on the function I've got. Yeah?
So one of the tutors told me that if you take the integral and then you plug it into u, you can have like a new set of intervals.
That was this whole thing. So in this problem, the other way to do this, just to show you, and actually let me sort of do it, not from the very beginning, but from right after I let the u's. So I'll be here. But then some side work I have to do. I have to figure out what these limits are for u. So u is negative x squared. So when x is negative 1, when x is 0, u is 0. When x is 1, u is negative 1. So now it's going to be from 0 to negative 1 with respect to u. And you'll get the same answer at the end. Because look here, what did I get when I plugged 1 in? I got negative 1 there. What did I get when I plug a 0? I got a 0. I'm going to get the same stuff when I plug those in. Yeah?
The book shows us how to do this using d of x instead of du.
Oh, it does. That's what I was worried about. I didn't even look to see what it did. So it solves for dx. And again, so if you're going by the book, it's good. That's fine. Just the trap you could run into. So, for example, that problem we had up here earlier.
This way is way easier than what you're showing it.
Oh, that's cool. You're saying that. I don't know if you're saying that just to humor me. But that problem we had earlier when it was like this. This is a perfect example. If somebody said u is 2 plus x, du is dx. So then they go, okay, integral. There's my u. Dx is du. And well, I'm just going to take that out or do something weird with that because they don't. This way doesn't make it very clear that this has to be involved somewhere. Does that make any sense? I should have checked, but for some reason I thought there's no way they're going to show that way. I didn't even look. That's not a really good example because there's no solving to do there. But like here, you would say dx equals du over negative 2x. Right? And that's really...
So for the one on the left, would it just be du of dx would be 1?
Where am I at?
What you got circled there?
Here?
Yeah, you're trying to solve for what?
Well, it's trying to solve for dx. And dx is du. So not the greatest example, but let me show you that number 60. Let me show you that way, the book way real quick. Make sure that you can see me at home. Oh, let me see. I've done too much in there already. All right. if I do this, I'm not worried about the u sub and the limits right now. I'm just worried about the one aspect you brought up. If I say u equals negative x squared, du equals negative 2x dx. So you can say dx equals du over negative 2x. So now I can replace negative x squared with u, and I can replace dx with du over negative 2x. So actually this is easier in a way because it takes thinking out of it in one respect. You don't have to think, you just put it in there and you just let things happen. And you know, see those cancel on this time it does. But it's when that's not what it needs to be, when it requires some clever manipulation of something, that this method makes people do wrong things. Right? So there's nothing wrong with the method mathematically. It's just that it kind of doesn't allow you to make things happen. It just kind of makes things happen subtly. It's not very explicit what's going on. That's why I really don't like that way, but I don't know if you guys are with me on that. You guys are all probably now thinking, what are you talking about math is subtle? What is this? I didn't know there's so many gradations of math. What is this crap? But yeah, that's true. Yeah?
As I've seen the book, it says that x dx equals to du over negative 2.
Yeah.
It's the way that book does.
Yes.
It doesn't
Oh, x dx.
Yeah.
All right, so that's a little bit better. I'm with you. So they at least they see what they have, and then you can replace, and that's fine. Yeah, that's basically the same thing. That's better. Okay, makes me feel better because I've seen teachers teach it where you just divide that down and just put it in, and you just hope for the best. All right, and that's not ever a good way to do it. But that's a kind of a compromise. So I like that. Okay. Thank you. Okay. So let's see, we did that problem about 4 times. That's enough of that one. Anything else from homework? Yeah.
27 from 5.5.
27?
Yeah.
Wait, this is a funny one. Not, laugh out loud funny, but it's still funny. What's definitely the inside function?
X cubed plus
Yeah,
3.
this is definitely stuck inside a 4th power. That guy's free to move around. This guy is stuck inside a 4th power. There's no question that's the u. That would be a chain rule piece for derivatives, right? So if u is x cubed plus 3x, what's du?
3x to the 4th plus
Careful.
x squared.
Derivative.
Squared.
Plus 3.
And I have that. Minus the coefficient. I have that in there, right? Yes. So if I put a 1/3 there, I have a 3x squared plus 3. You see that? So this guy's derivative is in here. So when I first looked at that, I knew immediately what the problem was, just because I've done a lot of these. So when I see that, I know it's good to go. Now the coefficients, they could certainly put one in there. The coefficients don't quite match, and that's going to be an ugly one that you would handle later by other methods you're going to learn in Calc 2 if you have to take Calc 2. If you never take Calc 2, you'll never know. And so you guys are okay with that. But there's a cube, there's a square. There's a x, there's a 1. I mean, and in that respect, they match. This is a very good candidate to be this guy's derivative. Because the degree is exactly 1 removed, 1 down. Now the only thing I'm worried about is, and I saw the 3 coming, there's a 3 there, so I'm good to go. Right? Same coefficients, bam. I knew it was going to work. So to finish this out, I'll put the 1/3 there, so I can put the 3 inside there. What's 3x squared plus 3 times dx? du. And how do I write the inside now? U to the 4th. Right, and then that's nice. So almost no matter what level of your math you're in, if you're using U sub, the main purpose of it is to make what you're working with look better. It actually didn't change the form of it, to tell you honestly. It looks different, but it represents the same thing. If u is this, then du is there. It's in there. So I'm just actually making it more, just kind of glossing over some of the details. Does that make sense? I'm not being as explicit with what u is, because I don't need to be. I just want to see the form of it. So then this is 1/3 times 1/5 u to the 5th. Oh, there was no. So this is 1/15 x cubed plus 3x to the 5th plus c. Cool. You can always check your work by taking the derivative. See if it comes back out. Alright, I gotta stop doing the whole problem. Let's stop. Some of you guys, I hope, feel the same way I do about it. It's kind of cool to see everything kind of come together. Now, realizing at the same time, this is very contrived to work. It's not saying that u sub is not useful. It comes up a lot. But u sub certainly is a very lucky thing to find. If I just write something down out of nowhere, if I put a 2 there in the beginning, I'm screwed. There's got to be another way to do it. Then I have to, at least FOIL that out so many times and then bring that in there. You with me? Then it's doable, just law. Okay. So, there's enough questions. We got to get into stuff. Unless there's any burning. Okay. Last time we did section 6.2. And we loved it. We loved it. Oh! Who should be keeping me honest? I promised I would do a certain kind of problem. You still want to see it, or you want to hold off till
We're talking about the
review day?
slide thing?
Yeah.
Yeah, that'd be nice.
Oh, so non-committal. All right. Real quick, somebody asked me to do a problem like the XI thing. Just to let you know, we are finishing up chapter 6 tonight, no matter what. So what I mean by that is if they ask you to do like, what do you got, Jeff? I don't know. Let's take something from the book so I don't get something that's really freaky. This is from section 5. Where'd it go? 5.2? I think so. Yes, 5.2. Yeah, here we go. Oh, there's a problem just waiting for me. I think we did that problem, though. Looks familiar. So if I do negative 2 to 0 of x squared plus x dx. And I would be very explicit like I did on the quiz. I'd say using, estimate this integral using this many rectangles. So it's very obvious what I mean. This one wants you to find the exact one. So on the test, I have to figure out a way to say that, but because this is just saying using theorem 4. But what I think I write on there is using this form of it. How would this look? Probably something like that. That, of course, replaces what symbol?
Big S.
The big SS. I like it. And then inside I've got, just to be more general, I have xi delta x. So this is, of course, the function. Delta x becomes dx. I get really, really tiny. Okay, so I think that's the way I'm going to say it on the test is evaluate this integral using this form. That's what I mean is to do what we're about to do. So what is delta x? Good. So it's b minus a. So it's 0 minus negative 2 over n. So it's 2 over n. What's the general xi? Good. So negative 2 plus 2 over n times I. Good. So the ith input, and this is something I said in my office that some people turn a light on. This is going back to when I say use 4 rectangles, 6 rectangles. This is like using infinite rectangles, right? But when I say use 4 rectangles, and I say left endpoint versus right endpoint, when I say left endpoint, that means if I have this function, let me make it a little more sharp, that height is going to be determined by the left endpoint being the input. So that function, if this is the left endpoint, let me use x1, x2. So this height would be based on x1. When I say right input and right endpoint, the height of the rectangle will be based on x2. That's all, right? So just in case that was freaking some of you guys out. This one doesn't really matter at all. Why not? Yeah, because the interval starts off delta x, but then it gets smaller and smaller. So no matter if I'm using midpoint, left point, 3/4 of the way point, who cares? It's going to eventually get down to just one option and the limit. Okay, so, and I was always going to do this, but now it's going to identify the kind of problem you have to do on the test, is this form. I give you this form. Fill it in. So I got limit, n goes infinity, sum I equals 1 to n. What's f of xi? What's xi? There. So what's f of xi? Yeah, so negative 2 plus 2i over n squared plus negative 2 plus 2i over n. So that is f of xi. Here's my function.
Don't you have to multiply by 2 over n?
Yes, I'm about to. I haven't gotten there yet. That's delta x.
Okay.
I like it. So that's f of xi. Is that cool? The function's given to you in the interval integration form. Delta x is, of course, 2 over n. Okay. And now it's really just, I think, I was telling some people in my office earlier that I think it's just the use of these symbols. You've seen some of these symbols before, but it's never been used quite this way. That we sort of don't realize that the mathematics involved here is actually not that bad. So, poor little dude. What's going to happen here? Let's see. Here I'm just going to have to FOIL that thing out, so I'm going to get 4 minus 4i over n plus, did I do that right? Plus 8. You be honest here, right? Is that cool? Just FOILing this thing out. So that squared, then negative 2 times this twice, right? And then plus the last guy squared. Plus negative 2 plus 2i over n times 2 over n, right? That part should be no problem. Just foiling. And now it's the like terms. Let's see what we got. We got 2 minus 6i over n plus 4i squared over n squared. Cool. How we doing? Is everyone with me? The heart of this problem is plugging this into that and then simplifying it. That's actually what takes up the most steps. Now I can bring that 2 over n in and split this up. So I'm going to get 4 over n minus the sum of 12i over n squared plus the sum of 8i squared over n cubed. Is that cool?
You
Yes.
broke them apart because they're not chained together.
Yeah, I can add all the 2's first, right? And multiply the 2 over n. And then I can add all these and add all these.
Oh, okay, got it.
So you're having a long string of numbers, and you add all the negative ones up, and you add all the positive ones up, and then put those together. So I can always, this is what's called a linear operator. It looks like I distributed it. And it's fine to think of it that way because that's what it looks like. I didn't. But that's what it looks like, so what the hell? Right? This is not this times this, so how could I have distributed it? But it looks just like I distributed it.
So would it have been wrong if you didn't distribute it? If you just distributed
No, you can still do it, but I want to break them up so I can really see the i's and my I squares, and I can use those expressions that I'm going to give you, right? Like the sum of I and the sum of I squared. Let me see if I remember. So this is the Gauss one. This is the weird one. This is the one I always forget. See, right there. I forgot. I know there's a 2n on the top, and that's what threw somebody else off. And, yeah, thank you. Okay, someday I might memorize that if I need it. Obviously, that hasn't come up very much in my life, because I haven't memorized. What about this first dude? Yeah, if I take a 4 over n out, which is completely fine because the variable for the summation is I, what's the sum 1 to n of 1?
1.
Yeah. And so what's, and then I keep going. Now these I'm going to get what I've just written down here. Limit, and go to infinity. Take a 12 over n squared out. Sum of I, plus limit. Take out 8 over n cubed, sum of I squared. Ooh, yeah. Oh, I put the limit by each one. That's why it took so long. Okay, so then I get, this is going to be 4n times n, so this is going to be 4. Is that cool? This is 4 over n times n. 4.
Where's the n come from?
Which n? Oh,
You just canceled out with.
if I add 1 up n times, if I have 1 plus 1 plus 1 plus 1 n times, that's n. Right?
That's n.
If I have, right now, how many 1s are up there? 4. What's 1 plus 1 plus 1? 4. So if there was n of them, the sum would be n. So this sum is n. Bam. So that's 4. I get the limit. And it goes to infinity. What's this guy? That's going to be this guy. Alright, so 2 goes into 12 6 times. The limit of this is... Well, it's that part's 6, but the limit of this is 1, because that's 1 n squared over n squared, so that's 1, so it's going to be 4 minus 6. And here's the part that messed somebody up. And as a teacher, it's really interesting when I don't realize I've only done one kind of thing, and then there's a little bit of a twist somewhere. So notice this has a 2 in it, so a coefficient on the top is going to be 2. So when I do the limit as n goes to infinity, what's the limit as n goes to infinity of this? 2. Because the coefficient on top is 2n cubed, right? 2. So it's going to be 4 minus 6 plus 4 thirds times 2, so 8 thirds. Good heavenly Lord. So then I get negative 2 plus 8 thirds, which is 2 thirds. Okay. The bulk of the work was just simplifying the inside. And then there was stripping away all the crap so I can see what I'm really summing. Right? Kind of with me? Sum of 1. Awesome. Sum of I. Sweet. Sum of I squared. Sweet. Right? Because I can pull everything that's a number in n out. Because that's not what the summation cares about. It's a constant according to the sum.
When you have the n2 bubbled with that n, parentheses n plus 1, are you saying that those cancel each other?
The limit as n goes to infinity of n squared plus n over n squared is 1 because the coefficient of the ratio of the coefficients. That's degree 2, degree 2. Degree 3, degree 3. What's the ratio of the coefficients? 2.
Oh,
Because the 2 there. Yeah. Okay, that was exciting. And of course, the quick way to do this problem is just, what's the integral?
1/3.
Okay, let's do over 3 plus x squared over 2 from negative 2 to 0. 0 is nothing, so then I get, so I get 0 minus negative 8/3 plus 2. It's like we'll just plug in negative 2 in. 0 makes it 0 minus, plug a negative 2 in to get that stuff. So that's going to be negative 8/3 plus 2 is negative 2/3. Negative that is 2/3. So this is like the limit definition of derivative versus just take the freaking derivative, right? Similar thing with integrals. This is where integrals are coming from. This is what they are built on. So we got to go through that. But then this is, of course, what they lead to. Just recognizing the pattern that they kept coming out to be the antiderivative. And that's how they connect. Okay. All right. So there's definitely going to be, I'm not going to put like 3 of these on the test. Just 1 of these on the test.
You'll provide the...
Yeah, the sum of I squared, all that kind of stuff here. Okay. So let's do some out of 6-2 first. And then we're going to get into 6-3. And I might just have to, we'll see where we are at that point. I just want to show you this. Here's 6-2. All right, here's a region. We'll do it this way. And I want to rotate this around the x-axis. So that I rotate it on the x-axis. So yeah, anyway. Right. Would have maybe been. Thank you so much. That was difficult to unfurl. Let's see. Any specific problem? I don't think you guys have maybe gotten into this yet. Possibly. So let's just pick one at random here. Actually, wait. Let's do this. Let's be a little more cautious about this. Let's do this. Let's do the region between y equals x and y equals x squared around the y-axis. And we're going to use, we'll have to see. It could be washers or discs, but those are basically the same thing. So I don't like the fact that I hate it when they make it sound like there's more than one thing. Washers are just when you have 2 discs that you have to subtract because you have a middle part that's empty. So a washer is just 2 discs. So it's really just a discs method where sometimes you have to subtract another disc out. Does that make any sense? Like the cookie cutter problem, right? So I'm going to use discs. So if I graph this thing, y equals x, and where do they meet? Y equals x and y equals x squared, they meet where? 0 and 1. 0 squared is 0, and 0 is 0. And 1 is 1. 1 is 1, yeah. And the parabola is going to be underneath. Okay, so there's the region that we're talking about. And I want to rotate that around the y-axis. Okay, so I want to rotate it this way. Which means my integral is going to be with respect to what? Good, so I can kind of put that down right now. Okay. So this officially is going to be a washer y, not just a disk. If I rotate this region around, so I get like this here. It's going to have, the inside is going to be empty. You with me? It's just going to be, I could actually put water in there to hold it. Right? The world's strangest cup ever, but still. So I know it's going to be a washer because it's got a middle part that's empty. If everything's got to be dy, what's the first thing I should do with these? This is kind of nice because that's either way. But this has to be a function of y, not a function of x. So this would be x equal to square root of y. I'm on the positive side of things there. I'm in the first quadrant, so I don't have to worry about making it negative. I'm good there. How are we going? Okay. So the whole point of this thing then, in general, is going to be pi times the outer radius squared minus the inner radius squared, because it's going to be the difference of two areas of circles, right? And I'm moving along the y-axis. So if I was here, for example, what would the inner radius be? And what would the outer radius be?
Inner radius would be the y over x.
Y is equal to
Inner radius is y. And what's the outer radius?
square root of y.
Good, square root of y. How we doing? Because what I'm doing is I'm moving along the y-axis. That's what this means. I'm moving along the y-axis. So at any specific point, my radii are dependent on where I am on the y-axis. That's why everything's got to be in terms of y, not x. And then when I rotate this thing around, I'm going to get a disk. I can never draw it as well as a book, but when I rotate this thing around, here's my half disk, right? So that's the outer radius making a disk. And then I've got to subtract the inner radius from that. So if I was looking down on top, it would look like that. So that's why it's called the disk method. And in fact, that's why it's called the washer method. But there's the disk, and I'm subtracting out the middle disk. That's all I'm doing there. How are we doing so far? This is all building off of the lecture from last time. So if you weren't here, this is not building off of much of anything. So let's see. Now if I throw everything in there, I get radius outer is square root of y, so I get y minus y squared from what to what? What's y doing? Here you can't go wrong, but in general you have to be careful. 0 to 1. They're both going from 0 to 1, but oh. Okay, cool. So then what do I get here? I get pi times. Let this part be easy, because it is. It's the integral of y. Yeah, y squared over 2 minus y cubed over 3 from 0 to 1. So I get pi times, here 0 is really going to make things 0, so I don't have to worry about it. So I get 1/2 minus 1/3, 3/6 minus 2/6, I get 1/6. I get pi over 6. How are we doing? Okay, cool. So in general, for the disk method, or the washer method, which are really the same thing, if I am rotating around anything parallel to the y-axis, it's got to be dy. If I'm rotating anything parallel to the x-axis, it's got to be dx. Now the most evil thing about the shell method, which we're about to talk about, is that that's reversed. Of course. Before I move out of this, any specific questions from this section? Again, I don't think anybody's done this one.
I think it's just me, but how'd you get the y squared over 2? Or in the y, I don't know what it's...
Yeah, just the antiderivative of y. Yeah. So, I mean, I understand when we're doing a lot of weird new stuff. That's weird. But let this part be.
Yeah.
As long as you set this integral up correctly, the rest of it should be easy. Yeah.
If we didn't have a 0, say that started at 1 and went to 2, and we actually had a big F of A, or a big F of B minus
2 and yeah.
big F of A, would you multiply the
Yes. By pi?
both of them?
Yeah. Oh yeah. You have to. Because this is pi times what this is. So to figure that out, then, if it was 1 to 2, it would be like a giant.
But I mean, you wouldn't work out the big F of B minus big F of A. You wouldn't work that out and then multiply it by.
Sure, you can, of course. Or you could bring the pi in from the first place and just have it everywhere to begin with.
No.
Either way, yeah. Okay. So the whole thing to realize, I really, what's going to help you do this is if you can draw a decent graph. Knowing how bad I draw, this is still good enough to help me set things up. That's all I need is a picture that's good enough to help me set things up. I didn't even need to draw this stuff over there. I really didn't need to draw this rotation at all. That was just for me. I can just work directly with that function, the two functions that they gave. Right? Because then here's what I'm flipping it around. That's the central axis. So the radius is going to be from there out. From there out. How we doing? Okay, yeah.
Could we do a problem that doesn't have the reflection across the axis? Like, so it'd be like y equals 2 or something?
Sure. Okay, let's do one of those. And about y equals something sounds good. So let's say, that looks freaky. Let's see what happens here. So this is number 13.
On which section? 6-2?
Yeah, sorry, 6-2. So I want the region defined between these two, and I want to rotate it about y equals 1. Okay. So a very quick sketch of this. And they tell me I want to go up to y equals 3. I want it to be bounded by y equals 3 and this function. And I want to rotate it about y equals 1. So of course the hard part, well, possibly the hard part of this is just graphing this thing. So what does secant look like? And then I have to do 1 plus secant. What does secant look like? What does it sit on top and below of? Cosine, because it's 1 over cosine, right? So cosine would look like this, right? I can be more specific here. So this will be pi over 2. This will be pi. Oops. This will be pi. This will be pi over 2, and then finally it gets back up to here at 2 pi. Okay, so that shall be. So in purple there is the cosine. So I can build secant off of that.
The slope is opposite, right?
Say again?
The slope is like opposite and it meets at the max and min.
Yeah, so basically the nice thing about secant is it just sits on top. So wherever this thing goes to 0 is going to be a vertical asymptote. So it's going to be like this. Now, of course, I got this plus 1 to worry about too, right? So this is the hardest little quick graph that I've had to do. So I've got to pick it up by 1. So let me put another one down here so I can... This is my working graph, and this is going to be my final graph here. So it looks like... so here I'm going to go up by 1. So it's going to be at 2. Right, because it's sitting on top. And then what's happening over here? Let's see. Is that all they tell me? That's kind of evil. I think I know what they mean. Yeah, they need to be more specific here. Oh, too bad for us. I'm pretty sure they mean just this, because otherwise it would be... Let me see if you guys get this. If I wasn't being very specific, and I just said integrate between 1 plus secant x and y equals 3, well, that would happen many, many, many times. This integral would be infinity, I'd be done. So that would actually be the nicer way to interpret this problem. What I think they mean... Yeah, they didn't. That's just stupid. Well, we're gonna guess what they mean. We're gonna guess that they mean this here. Right, actually not that there. I gotta pick it up by 1, so it's gonna be there there. So now I got to figure out what these points are. How we doing? I'm going to rotate that around y equals 1. Okay, so don't get hung up on that. You can always do this in the graphic calculator real quick and just see what the hell it looks like. Nothing wrong with that. How do I see this point here, what this point is here? I know it's 3 on the y-axis. What is it on the x-axis? Just in case I need to know. Yeah, well, how would it be pi? Why would it be pi over 2?
Because cosine 0 pi over 2.
Cosine 0 pi over 2, I know.
But 1 over
Which would mean that would be infinite there.
Yeah.
That's not good, right? So, let me not do this here. All right, what I'm trying to say, here's my asymptotes. My asymptotes are out here at pi over 2 and negative pi over 2. Cool, that's my asymptotes. That's where the cosine is 0. I just want to know where it hits the y equals 3 line, because I'm trying to figure out my region. It's between y equals 3 and 1 plus secant. So I want to know what the boundaries are on that region.
Set 1 plus secant to x equals 3.
Yeah. So 1 plus secant x equals 3. Secant x equals 2. Cosine x equals 1/2. So it's got to be what angles? Or what reference angle? Let's start there.
Pi over 3.
No, over 6.
Cosine is small when it gets far away from the x-axis.
Goes to pi over 6.
Pi over 3 is bigger than pi over 6. Right? Pi over 6 piece is smaller. Yeah, so pi over 3. Get closer to the y-axis to make cosine small. Cool. So at pi over 3, this is going to be pi over 3, this is going to be negative pi over 3. Okay, how are we doing so far? That's the work just to define my region that I'm going to rotate, right? And what's y going from to? Y is obviously going from 2 to 3. Okay. All right, so since I'm rotating it around y equals 3, the integral is going to be d.
Rotating around y equals 1.
Y equals 1, yeah, thank you. So let me take this out here. Rotating around y equals 1. I'm rotating around y equals something. That's parallel to the x-axis because it's integral dx. I like it. So in this region, and dx, of course, now I see that I needed to know this. X is going from negative pi over 3 to pi over 3. You could even say, well, no, I can't. Well, yes, I could, but let's not do it. You could use symmetry here to change this a little bit, but I'm not going to. So from negative pi over 3 to pi over 3, what's my... So for any given x, and once you know it's dx, look at any given x, just start drawing from there. What's my inner radius?
Secant x.
1 plus secant x. And my outer radius is, of course, 3.
Isn't that minus 1? Both of them?
Yeah.
Oh, yeah, thank you. I keep forgetting we're rotating around the y equals 1. All right, so here's my thing there. So I actually got to start from here. So yeah, so minus 1. I like that. And then 3 minus 1, 2. So this is secant x away, and this is 2 away from 1. The line that I'm actually rotating around. So your radius has always got to come right off of that axis. My axis is y equals 1. So you're right. Everything's closer now because I've lifted my axis up from that I'm actually rotating around. So I'm closer. I'm one step closer to both of those. So where do those come into play now? Yeah, so what's going to be on the outside? Pi. And then I've got my 2 areas that I want to subtract. Outer radius squared minus inner radius squared. So the step I pretty much leapfrogged over and you guys brought me back in was the whole point of this problem. Somebody wanted me to do one where the axis was not the x or y axis. In that case, you just got to put your radius in terms, how far away is it from that axis? Right? This is above that, so it's going to be 3 minus 1 and 1 plus secant x minus 1. We learned that last time. It's always a bigger one minus a smaller one. So now I just got to integrate that, and it's not too bad. Right? Secant squared is not bad either. So I get pi times 4x minus tangent from negative pi over 3 to pi over 3. And you just plug and check. And if I put a problem like this in the test, I'm definitely going to say I want the exact form, not the approximate form. I don't want decimals, because that's something you should know the tangent of. So if I do the first part, so this is 4 pi over 3. What's the tangent of pi over 3? So tangent is sine over cosine. So yeah, sine's bigger at 60. So square root of 3 over 2 over 1/2, so square root of 3. I like it. Minus, put a negative pi over 3 in there, so I'll get negative 4 pi over 3. And what's the tangent of negative pi over 3? Yeah, negative square root of 3. So then I get, let's see here. I get pi times 8 pi over 3 minus root 3 plus, what is going on in there, Jeff? Minus negative, yeah. So minus a minus a negative, so that's minus, so minus 2 root 3. And I can bring my pi in. So that minus is from there, that minus is from the evaluating that, and that minus is, of course, from the fundamental theorem, the f of b minus f of a. Okay, so the disk and washer method, let it be nice that if I'm rotating around something parallel to the y-axis, it's dy, it's parallel to the x-axis, it's dx. That's nice. All right, so two things I want to do to get us into the next section. I want to leave this here. Is that the one? Yeah. I want to leave that there because we're going to do this one over again with the new method. If you didn't get everything you wanted from that one, get it now. Everybody got what they want here? More than you wanted? Okay. So the whole idea of cylindrical shells, this is kind of neat. And the one thing about cylindrical shells, so the main idea of discs and washers and stuff is to, if I'm rotating around the x-axis, then it would be the radius, and then I would rotate, and I get this disc. That's why it's called the disc method. The cylindrical shells method would take that same thing, and it would try to figure out, it would actually, instead of doing the radius at a certain point and then adding up all the areas, so as I move along, my disc is going to get smaller towards the ends. You with me? Because the radius keeps getting smaller and smaller towards the ends. The shell method says, screw that. Let me just go along the whole body of this thing. And then when you rotate it, I end up with these cylindrical shells. Hence the name. It's crazy. That's not bad for me. For me, that's really good. Sure. And then what I would do then is I would move up and down the y-axis and just do another shell here and then rotate that. So you have all these like interlocking shells in each other. All right, so thankfully, you don't have to rely on my drawing alone. That would be cruel and unusual punishment. So let's say I have this region here. Right? And so they're looking at, I can make all these little rectangles. That looks a lot like Riemann's sum for just finding the area of that by itself, right? So the really cool thing is this is cylindrical shells is actually kind of cool because it's so related to Riemann's sums. The only new thing is I'm going to rotate each one of these. So if I and this is not the best thing. I wish they would do this. Let me put the cylinders back. So if I look at this, you can see all those cylinders. So if I decrease the number of approximating rectangles I use, let's see if I can show you. So you see how there's cylinders inside cylinders inside cylinders? So it's instead of slicing and then adding up all those areas of those slices, I'm approximating the shape by using these shells that are actually built off of these rectangles we've used before. Just take a rectangle and rotate that bad boy. Right? Now please realize this is a cutoff. It should go all the way around. But just so we can see it a little better, they've stopped it. So of course if I increase my approximating stuff, it gets better and better and better. Just can't quite see it as well as I wanted to. So let me take the solid. Sweep that out. So here's the solid I'm trying to approximate. All right, looks like a Bundt can. You ever seen those? Bundt cake things? Can you guys get the impression of that? It's got like it's just that same shape, just rotated all the way around, right? So now if I go to the cylinders are trying to approximate that shape. And they do a decent job, and it's not many rectangles. So of course, the process would take that to infinity. So if I start with, let's kind of break this down a little bit. Let me make this more like that picture up there. So if I've got this, and I'm trying to use cylinders, and I rotate that bad boy around, so I get that cylinder there. That's half of it, of course. It didn't go all the way around. So if it did go all the way around, I'm not going to try to draw that. What would the volume of that be? So let's look at this. Let me. If I did complete this whole thing, it would look like this, with a piece cut out of the middle, right? Again, for me, not that bad. You kind of with me? So there's a thickness to it that actually we're going to do something that sounds kind of familiar. We're going to use, let's see, inner radius, outer radius. Now just go with me. This method is actually nicer than the other one. This is, you gotta trust me. I can see a few of you guys are like, this is so awesome, Jeff. So this is my inner radius. Oops, yeah. This is my inner radius here. My outer radius there. This height, of course, is going to be dependent on the function value, and what we end up doing is, let me see here. Let's do this. What's the volume of a cylinder? Any just cylinder sitting there? What's the volume of it? 11. Cool. So take the circle and then just repeat it H times. That's the volume of a cylinder. So the volume of the shell is going to be the volume of the outer shell minus the volume of the inner shell. Is that cool? And actually, let me do this so I can make this a little bit more like what I'm used to here. We'll call this one, I think I can work with it. Let's see if I can work with it. Okay. What would this volume here be? The outer shell. So let's say this is the height. There's the radius. What's its volume going to be? Yep, R0 squared H minus. I love it. So far, so good. And then this is going to be, if I kind of factor this out a little bit. Go with me. If I factor even more, can you factor it even more? This, of course, is just a difference of squares. So then if I do this, now here's the part you got to go with. Right, so what the hell did I do that for? Right? Because this is the thickness of it, right? That would just be this, what I'm going to call delta R. This is kind of like my xi, right? So I've got like R, it goes from Ri to Ro, it's here. My rectangle is from Ri to Ro, is that cool? So this is the average of those two things. It's the midpoint, in a way, of that rectangle. You with me? It's the midpoint of that rectangle. Okay, sort. So I get 2 pi h. This is my delta r. And this, I'm going to use just the letter r, because what happens... Oh, I don't know if you guys are with me now. When we did Riemann sums, and we used xi, what happens to... oh, I just took it away. I said it didn't want to. When we have this here, what happens here? This just becomes integral. This becomes f of x, because these end up having one choice. You know, it's not a specific thing in there. It's just going to be x all the way along. If I use an infinite number of rectangles, I don't leave any inputs out. I use every single input. So in the limit, we're going to take a limit of this. I can replace that with just r. It's something in between Ro and Ri. But if I let my shells go to infinity, there's just going to be one choice, r. I'm going to have to let r go from hit every value that it can. Now, what's interesting about this? Two pi r h. I don't know if you guys know anything about that. So let's do this. If I take this guy, so you guys can do this in your head, and I chop through and bend it, right? Thankfully, this thing is not made of steel. It's something flexible, right? So it's like a paper towel inside, and I just cut one side and open it up and stamp it out, so it's flat. You with me? So this would look like this. Really, really, really overdone here. Okay. So cool, just cut it and then open it. Bam, there it is, right? So what is this? H. What is this? 2 pi r. That's the circumference. I love it. And of course, what's this? Delta r. That's the thickness of it, right? So what would the volume of this thing be? Well, the area of this face is 2 pi rh, and it's repeated delta r times. Okay, maybe. Okay. Yeah, okay. When you want to get the total volume, then you're going to sum up all of your little volumes from all of your, what am I trying to say? You're going to sum all these up. The infinite sum of all these different volumes of your shells that you're going to make. And now, the thing about the height, what is that height really going to be?
Output of the function.
I love it. The output of the function at that point. So in the case where I'm doing, how did I do this? Oh, good. If I'm rotating in this direction, then it's going to be dependent on x. Now, that's the part that's really freaky. I'm rotating about the y-axis, but when I do it with shells, the radius is actually dependent on x. So this is going to become f of xi in this case. So if I do this limit, the volume becomes the integral 2 pi r f of x And what's the R going to be, really? That's where I got to be careful. What's R going to be?
R0 minus R.
Not what does R go from to, but what is R? What determines the radius in this case? How far out do I have to go?
Oh, whatever that.
Along this axis, that's the x-axis. So then I get that weirdness. So this part is the circumference. Now just stay with me now. You know, derivation is never pretty, right? But you just, I want to point out now what it is you want to look for in a problem. So let me point out real quick what each piece of this is. That's the circumference. That's the height. And that, of course, is the thickness. So it's still, you can still see the physical properties of that thing right there, right? Or even better, this thing here, right? Circumference, height, and then the thickness. That's what makes this a volume in there. And if we're going to add up all the volumes, I'm golden. So this is kind of cool. The washer method, you add up a bunch of areas to make a shape. Here, I'm adding up a bunch of volumes.